Okay, now that we've done that, let's talk about different types of energy that we have, okay? Different types of energy. Because what you probably don't realize is that you are dealing with energy right now. Like right now in your life, energy is all around you, and anything that you're doing that has electrical power going into it is dealing with energy as well. So you're like, okay, well, that's electrical power. And you're correct. But honestly, all that is coming from heat at some point. In most cases. Okay. Now let's talk about the different types of energy you might see and where you might care about thermodynamics. So, first one, your refrigerator. This was a pretty obvious one. You're like, okay, heating, well, on the opposite side, cooling is all about thermodynamics. Your fridge works because on the back it has these coils usually. Those coils have a liquid in them, refrigerant of some sort, that is going from being a liquid to being a gas. There we go, that's my gas. When it does that, it steals heat, okay? It steals heat. What does it steal it from? Your food, the air inside your fridge, and then it expels that outside of your fridge. So that's number one. That's the first place we're seeing thermodynamics in your everyday life. Okay, do you like boats? I like boats. Well, they deal with thermodynamics too because they have an engine. If they have an engine, which they have to get something spinning to make them move, woo! That engine is most likely burning gasoline, and that gasoline produces power using thermodynamics. How does it do it? Well, at its basic, we have some sort of piston-like device usually. We have, and it's not a liquid. I'm drawing the gas if it's a liquid. They spray it in, or it comes in as already mixed, and then suddenly we have this gas of air fuel. We light it on fire, it explodes, and now wait a second, it's gotten hot. When it gets hot, it pushes that piston up. That does work. That work happens over time, which gives us power, and it spins the propeller or whatever it is and gets the boat moving. Okay, very similarly, wrong one, sorry, looking at nuclear now. So this is nuclear, like, well, that's nuclear. That's completely different here. Not so much. Because if you go inside one of these nuclear power plants, what you'll find is a big vat of water. Way down in there. And inside of that water, way down, you'll see some little rods. Those are fuel rods. They're made of uranium or plutonium, various highly radioactive, kill you if you get near them kind of things. And what they're doing is they're constantly shooting off little neutrons like machine guns. Okay, there's neutrons just flying out of them as they decay. Don't worry about what a neutron is. If you don't know, that's okay. The big thing though is, since they are shooting out those neutrons, what's happening is those neutrons are bouncing into water molecules. Okay, so I got a water molecule right here. A neutron bounces into it. This water molecule moves faster because of it. And when it moves faster, that means that its temperature has gone up. Oh my goodness, temperature is going up. It is causing the water around it to heat up. And that hot water then is used to move pistons, to move turbines, to spin, to cause power. So heat is still there. It's still a part of it. And there was also a plane. I would have loved to talk about that because I'm an aerospace engineer, but apparently I didn't put it in here. That's okay. Okay. Now, we see that energy is everywhere, and there's lots of different types of energy. But now if we're going to talk about energy, we're going to have to come up with a way of doing it so that we can be consistent, so we can talk with somebody else about what we're doing. Because I could tell you that, it's Cheetos, it's 15 Cheetos outside, and the rain is coming down at a rate of 14 dogs, but that doesn't mean anything to you. It doesn't mean anything to me. But I have to have a consistent way of talking to people. So we're going to be defining dimensions and units. So any physical quantity can be characterized by dimensions. Dimension is simply something that you can describe. Things like, you use descriptive words like heavy, okay, or light, far, near, long, short, hot, cold. Those are the words I use to define dimensions because they're quantities that can be described, that can be compared, but dimensions by themselves don't have any numbers. I can't say it's been 3 times since I saw you last. You don't have any idea what I'm talking about. Dimensions are just things we can describe. Now, if I want to talk to you about how long, heavy, light, far, short, near, hot, or cold something is, I attach a unit to it. A unit is a particular amount of a dimension, like a foot or a meter, a second. All of those things are units. Now we have basic dimensions and we have also derived dimensions. Basic ones and derived ones, it's not super important, but the big thing here is mass, length, and time are what I use to determine velocity, energy, and volume. Notice 2 V's. Yes, they do that to you. So, like, velocity is distance over time. So I'm taking 2 basic dimensions, taking 2 fundamental dimensions, and using it to make a derived dimension. Why do you care about that? Because if you actually master understanding fundamental and derived dimensions, you can actually write the equations for a lot of things that you don't even know. I did it once on a test. It helped me. So don't knock it. Okay, now, like I said before, dimensions are qualitative. I can describe them with all of these words, but if I want to add some numbers, I need units because those are quantitative. And we've got 2 systems for them. We have the metric system, which is simple and logical. That's kind of like throwing shade at the English system, but it deserves it. Simple logic, based on decimal relationship between various units. Mostly it's based on water, okay? Like that's where it all comes from. Water has a density that's 1,000 kilograms per meter cubed. Nice round number. It's technically 997, but it was 1,000 until they realized they were slightly off. Water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. Wow, all these nice little numbers. So everything's based on water. That's what they do it for. Why? Because you deal with water all the time. Like you've probably taken a shower or a bath sometime in the past few weeks. Hopefully. You drink water, or you should drink water. I should drink more water. Note to self, drink more water. Okay, English system is different. And your book throws a lot of shade at it, but I'm going to give it a slight bit of slack. Like some things are weird, like why is it a foot? Well, because at one point it was actually based off a person's foot, okay? Like they had a foot, they measured it, that was how long a foot was. Eventually they standardized it. So we don't have those, we don't have to measure any king's foot. King Charles did not affect anything when he became king in England. So we're fine there. But there's also the temperature units, which are Fahrenheit. And for temperature, it's 212 degrees Fahrenheit for boiling and 32 degrees Fahrenheit for freezing, for water. And so most people are like, this doesn't make any sense. Why is it so random? It's not, honestly. The person who made it said that 0 degrees Fahrenheit is more or less frozen seawater, okay? Think of the ocean. That's when it gets frozen. And 100 degrees Fahrenheit was supposed to be your body temperature. They realized later that it wasn't perfectly accurate because you're actually 98.6. It changes over time. But he was doing a range of temperatures that most people would experience. Like 100 degrees Fahrenheit is really hot. 0 is cold. I don't experience 100 degrees Celsius or 0 degrees Celsius I see a lot, but 100 degrees Celsius I don't actually experience. So he was trying to give a range of temperatures that made sense to most people. Okay, but with all those issues, the reason the English stopped using it, I am incredibly biased towards the metric system. So please check that out on your own time. Okay, now with that, we're going to be going into an example next time where we learn about conversions, how to go between the 2 systems. So check that out because you do need to know how to convert. And there's a lot of stuff in this chapter about all the different units. I'm not going to really stick on that too much. You can read the chapter, but I will do some conversions to show you how to go back and forth and work with some of the units here. So see you all next time. Have a great day. Bye-bye.